The next spotlight will be binary classification from positive confidence data, presented by Takashi Ishida.
Hi, everyone. Today I'm going to talk about binary classification from positive confidence data, and this is joint work with Ganyu and Masashi Sugiyama. So if you think about the ordinary binary classification setup, I think you usually have both positive data and negative data, and then you can learn your binary classifier. However, in real-world applications, sometimes you cannot collect any negative data, and you can only collect positive data. So here's our research question. Can we learn a binary classifier from only positive data? This means we do not have any negative data, and we do not even have unlabeled data. This seems like a very difficult task since we do not have any information about our negative distribution. For example, we would not know the direction of the negative distribution compared to the positive distribution, as you can see on the lower figure. So you might be thinking about one-class classification or anomaly detection. These methods describe the positive class by, for example, clustering-related methods. However, they cannot tune the hyperparameters for maximizing the generalization ability, and their aim is not on classifying positive class and the negative class. You also might be thinking about positive unlabeled classification, which use additional unlabeled data from the marginal distribution, as you can see in the lower figure. They also assume that the class prior, Py, is known, and you need this beforehand. This is nice because they aim for classification, but we want to think of the scenario where we don't even have access to the unlabeled data. So what should we do if we only have positive data and we still want to do classification? So here's our main idea. Even if we only have positive data, sometimes we can attach a confidence score to each one of them. So I'll give you a very simple example. Let's say you're trying to think of a dog versus wolf image binary classification problem. Then you'd only have dog images since you only have access to the positive data. But for each of your dogs, maybe you can attach a confidence score. For example, one of your image might be like 95% dog, another one might be like 80% dog. On the right-hand side, we have a figure. The darker colored samples show the ones with high confidence, and the lighter colored ones are the data samples with low confidence. If you're given this kind of situation, I think you could imagine that your binary classifier would be somewhere in the lower right-hand side, as you can see with the black line. So this is intuitive. It might work somehow, but a more important question is, can we really learn a good binary classifier in this way? So the main message in our paper is that if you can equip your positive data with this kind of confidence, which we call positive confidence, you can actually learn a binary classifier with optimal convergence rate. So this was previously impossible when we only had hard-labeled positive samples, but since now we have the extra positive confidence information, and this includes the information of the negative distribution, and conceptually this is allowing us to discriminate between the positive and negative classes, even if we only have positive data. So we call this the positive confidence classification, or PConf classification for short. So let's go into the details a bit more. In binary classification, you usually want to do empirical risk minimization, or ERM. You train a binary classifier G so that the classification risk R is minimized. And the definition of R is given in the first equation here. But there's a big issue here. We do not have data from PXY. You can see in the definition of R that it uses the expectation over PXY. So we cannot simply do ERM. What we do have is we have positive data equipped with confidence. So we have a lot of pairs of Xi and Ri's, and Xi is the positive data drawn from the positive distribution, and Ri is the equipped positive confidence given by the positive posterior, because positive confidence is supposed to show the positiveness of that data sample. So our main contribution in the paper is that we showed that the classification risk can be expressed as the following inside this theorem. Basically, this is showing that you can do ERM with only positive data as long as you equip positive confidence to your positive data samples. And this leads to a theoretically grounded way of objective function design for your PConf classification problem, and you wouldn't need any negative data or even unlabeled data. So to summarize the paper, we proposed a novel setting and algorithm for classification from only positive data equipped with confidence. We established an ERM counterpart to binary classification for this setting. In our paper, we have a lot more work. We have some potential applications. We have experimental results. If you're interested, please come see our poster at number 97. Thank you for your time.